Okay, so earlier we talked about what an angle bisector is. We remember that it's a ray or a line segment that divides an angle into two congruent angles. So if I'm looking at this triangle here, triangle ETR, specifically at angle T, angle ETA, and angle ATR, they are marked as congruent. So that's how we know that segment TA is an angle bisector, because it's bisecting angle ETR. So we are also given some information here. Let's take a look at this example. So in this triangle, we just said that segment TA bisects angle RTE. We're told that the measure of angle RTA, this one, that it is 2x minus 25. And then we're told that the measure of angle ETA, this one, okay, so the two angles that are being bisected here, I didn't do a great job of highlighting that, but so we're given the measure of those two angles. So we know that if the larger angle, angle ETR, is being bisected, then the two smaller angles, the ones that were just mentioned, RTA and ETA, that they're congruent. So if they're congruent, that means they have the same measure. So what we're going to do is set their measures equal. 2x minus 25 is equal to 3x minus 50. And we'll solve for x. And remember, when we're solving for x here, we are talking about angle measures, so we'll have degrees. So I'm going to subtract 2x from each side, which gives me negative 25 is equal to x minus 50. I'm going to add 50 to both sides, which gives me 25 is equal to x. And remember that those are degrees. So that was x, but I'm supposed to find the measure of angle RTE. RTE, the large angle. So RTA and ETA, they should be congruent. So I'm going to go ahead and substitute x back into one of those. It doesn't really matter which one, and figure out what the measure of one of those equals, and then we'll just double it because those two angles are congruent, because we want the large angle, angle ETR or RTE. So I'm going to just substitute back in to find the measure of angle RTA. So that is 2 times, we just got 25 was x, so 2 times x minus 25. And when I do that, I'm getting 50 minus 25, which is 25 degrees. So the measure of angle RTA is 25 degrees. So I'm going to double that because RTA and ETA both have measures that are congruent. So they both have 25-degree measures. So I'm going to double that to get the measure of angle RTE. So the measure of angle RTE is twice 25 degrees, which means it equals 50 degrees. Okay. Next. So we looked at the point of concurrency in triangles that had medians drawn. Now we're going to take a look at the point of concurrency where we have angle bisectors drawn. So first of all, in this triangle here in our diagram, we have some angle bisectors. So segment PG is an angle bisector for angle HGF. So I'm going to go ahead and mark that. Okay, and then segment FP is an angle bisector for angle GFH. So I'm going to go ahead and mark that. And lastly, segment HP is an angle bisector for angle FHG. So I will go ahead and mark that. So now that I have all the angle bisectors marked, let's take a look at this point P. So where the three angle bisectors intersect, that point of concurrency here in a triangle is called the incenter. Okay, and if you recall where the median point of concurrency was, we called that the centroid. For angle bisectors, it's called an incenter. Now, the special fact about an incenter is that it is equidistant from the three sides. Okay, and remember when we're talking about distance, if you recall when we looked at the distance formula, the distance, when it's saying equidistant, meaning if I start at the incenter, that red dot there, if I start there at the incenter and I'm calculating the distance from the incenter to the side of the triangle, let's just look at from the incenter to segment FG for a moment. We're talking about the segment that is perpendicular to the side. Okay, so that's what they're referring to when they're saying from the side to the incenter. So if I do that on all three sides, so if I go from P, which is the incenter, straight down to the side of the triangle, that would be perpendicular. And I'm going to do that one more time from the incenter, point P, directly perpendicular to segment FH, the other side of the triangle. So now I can see that I have those three distances there. They are equal or equidistant. Okay, I'm going to call that point from the incenter P to side FH. I'm going to call that point T. I'm going to call the point from the incenter point P over to segment FG. I'm going to call that U. And I'm going to call this point here from the incenter over to segment HG. I'm going to call that S. Okay, so we know that those distances, TP is going to be equal to PU is going to be equal to PS, because the incenter is equidistant from the sides. So if we're looking at those three distances, they would be equal. So let's see how we can use that information. So it says the figure above shows triangle FHG with its three angle bisectors. Okay, so we already talked about that, and they're intersecting at point P. Remember, that point is called the incenter. So PT is equal to 1. Okay, and FT is equal to 2. Find PF. So I'm noticing that everything they're referring to is in this triangle right here. So I'm just going to redraw that triangle. So I have a right triangle. F was the top, and T is here, and P. Okay, and I'm going to put my 90-degree angle. Now I'm going to label just that triangle because it was starting to get confusing in the diagram. So I'll label just this triangle with what I know. So PT, the length of segment PT is 1, and FT is 2. And we're supposed to find PF or FP. So we can see now we have a right triangle and we want to find the hypotenuse. So we have the two legs and we want the hypotenuse. We know to use the Pythagorean theorem, which says leg squared, 1 squared, plus leg squared, 2 squared, is going to equal the hypotenuse squared, which we'll call C for right now. So 1 squared is 1 and 2 squared is 4. Whoops, I want a plus sign there. And that's going to equal C squared. So we have 5, which is equal to C squared. And I want to solve for C, of course, so I'm going to take the square root of each side. So C is equal to the square root of 5. So the length of PF is equal to the square root of 5. I'm going to leave that exact, but I could certainly use a calculator and approximate that if I wanted a decimal approximation. So that is the length of PF.